Okay, so this structure is known as the Voronoi diagram. And what it's done is I've divided the plane, divided R2 into regions so that if a query point comes in this region here, this will be the closest point. So I've predefined this region. If it comes over, and you know, these go off to infinity, and that's kind of okay. If you have more and more points, most of the regions start to look enclosed, but you know, it takes like 20 points before most of them look like that, and that'll take too long to draw. So if the query comes here, this is the closest point. And if I can figure out which of the regions I'm in, then I already know this must be the closest point. Okay. And so it turns out you can construct you can construct in O of n log n time, or at least expected time. I think you can do it deterministically, but that's too difficult to do in practice. There's a simple randomized algorithm to construct it. It takes O of n space, so it takes roughly the same space as the number of points that you have, and you can do O of log n query time. So there's a way to kind of build something that looks like a binary tree on top of here, so you can do queries to figure out which region you're in log n time. But this only works in 2 dimensions. Now by space I mean the number of edges. Now if you think about it, there are n points, so there could be n squared possible edges. Right? Each edge corresponds to a pair of these points. But I'm not going to draw all of them. It turns out you only need to draw a linear number of these edges. There are only so many close by points. And so this is kind of a fairly fascinating fact, but it doesn't work in 3 dimensions. In 3 dimensions, the number of edges you have to draw is going to be roughly n squared. In practice, maybe it's not so bad if your data is well behaved, but definitely in maybe 5 dimensions and above, you're going to have way more edges than you want to draw. And in fact, in more than 2 dimensions, you don't just need to keep track of edges. Edges are defined by 2 points. You need to keep track of where 3 points are equal distance, or where 4 points are equal distance. And it becomes much more complicated. The complexity in space is n to the d over 2, the ceiling of this. So it's going to grow exponentially with dimension. This is the space complexity. There are some techniques in 3 or 4 dimensions. You can kind of get this sort of thing to work with a lot of extra fancy stuff, but this only works in 2D. Yeah.
By edges, you mean hyperplanes?
What?
By edges, you mean hyperplanes?
Yeah, so you're going to have think of if you're in a 10-dimensional space, you're going to have a set of points where the same 7 points are all equal distance and no other point is closer. And so this is a 7-dimensional, no, I guess there'll be a 6-dimensional subspace. And it's going to be a subset of that. So that its boundaries are going to be 5-dimensional subspaces. Those 5-dimensional subspaces are going to have boundaries that are 4-dimensional subspaces, and it gets complicated. So this gets really complicated in higher dimensions. So you can't generalize this technique where you divide up the space in an efficient way more than 2 dimensions. But we can do something where we do something like this tree, but we're going to have to, we're not going to be able to directly get the answer. We're going to have to kind of do some extra work. So the next range of dimensions are, say, d is in between, say, 2 and, say, 12. So this is going to work up to roughly 12 dimensions. Maybe 8 to 20 depends on how nice your data is. And I'll talk about what it means for your data to be nice. This is going to be, there are various structures here, and I'll start by, I'll spend most of the time on something called a KD tree. So KD tree does not have the best kind of theoretical bounds, but it really works the best in practice for Euclidean distance, or some variations on it, which we'll discuss towards the end of class. Okay, so who's heard of a KD tree before? Okay, so roughly half the class. Okay, so I'll tell you again about it, and then but later on we'll see extensions of the KD tree, which you probably have not heard. Okay, so we're going to start by the set of these points. All right, okay, and so how the KD tree works is I'm going to build kind of a binary tree type structure here, but there's one dimension I could split the points to. So this is going to work top down. Before there was one dimension I could split the points on. Now I've got, let's just look in 2D, there are two dimensions I could split the points. So what do I do? So I pick one, I'll pick say the x direction, and I'll split the points into two sets. Okay? And then, now I've got, and this will correspond with, I'm going to call this node 1, and this will be a 1 in some data structure as well. So then, on each of now I have two halves of the points, I have two subtrees here, and in each of these, I'm going to split the points. You can have this go through one point or pick the two nearby points and pick the median, but these splits are not necessarily in the same spot. Okay, so represent this split as value 2, value 3, and I'm going to have these nodes in the tree. And then after I've done this, I'm going to cycle through all of the dimensions of the space. So if I had 3 dimensions, the next thing I do is I split the third dimension. But if I've gone through all of my dimensions and I'm in 2D, then I'm going to go back to the x dimension again. And again, I will split the space here and here, and this case here and here. So let's say I have, this is 4, 5, 6, and 7, and these correspond with 4. Okay. And so then each of these, so this quadrant here now corresponds to this edge of the tree. Okay, and so each of these now correspond with 1 point. I can stop when I have 1 point, or sometimes it makes sense to stop when you have a small number of points, and instead of building out the tree explicitly. So maybe you stop when you have 10 points in your set. Okay. So this is how I've split this. Yeah.
So if you have 3 dimensions, would each parent have 3 charts?
No, typically you only have 2 charts, still a binary tree. But so this was an x split, this is a y split, this is another x split. If you had 3 dimensions, it'd be x, y, z, then x, y, z again. Right, so this is x split, y split, x split, and keeps going. Yeah.
And each split just split the value in its own area, right?
Yeah, yeah. So each of the areas, each of the cells are disjoint. The cells are disjoint, and you choose the split so you have an even number of points on either side. So roughly the same size. So that means the height is going to be logarithmic, the same as over here.
So in this picture, we only have like 8 points. So we just split one round of x, y, z.
And then it's done. Yeah, but if you have 1 million points, then you're going to need log of 1 million levels.
Okay.
Right, so the height of the tree is how many split rounds you need to do. And if you're dividing by the points half of each time, then you need a log of 1 million. So a log of 1 million was at, like 13 to 20? 20? Okay, so log of 1 million is 20, and that's, you have 20 levels. So if So if before in the binary tree here, it would take 20 steps to search for the nearest point out of a million. You know, this is a big win over checking every one of the points. I don't want to check every point. I can do 20 comparisons and get to the closest one. So I want to do something similar here. But I don't quite have as nice of a structure. All right, so let's see how this would work. Let's say my query point is here. Okay, so how's this going to work? I want to find the nearest neighbor. Well, okay, let's first do kind of the obvious thing. Let's follow this technique. I want to find the cell that contains this query point. Okay, so it's going to be going to go down this side, and then on 1, it's on the right side here. On 3, it's on the side here that goes towards 7. Right, it's on the 7 side. And then it's going to split this way. So I'm in this region. And this corresponds with this blue point. So now I'd say this blue point could be the nearest neighbor. Well, it turns out it's not, right? Nearest neighbor Euclidean space is defined means that if I draw a ball around this point that is at a distance to this nearest neighbor, that the ball should be empty, except for this point in the boundary. But that's not true. This point is closer. I've done something. Let me draw this ball a little bit. Let me fake something a little bit. All right. So let's say that this is the ball. But this is good. So I've gotten some candidate point. I think this point might be the nearest neighbor. And so now this point, I know this point is pretty close. I've found a point which is fairly close to it. No point else in this cell here, is any closer. There's only one point. Okay, but now I want to say that I can filter out part of the tree I don't need to check. My goal is to not check every single point. So what I do is I say, well, now that I have this witness, which gives me this ball here, I want to go back up the tree and verify I haven't missed anything. Okay, so what do? Well, I go back up to level 7 on this split, and I say on level 7, could there be any point on this side of the split that could have been closer than the point I found? Let's call this point P. This one. And I say, well, this ball does not intersect this line here, which means there can't be anything closer over here. So that means on 7, I can mark off this whole subtree. I don't have to check. Now there's only one point, so it didn't really save me much, but let's keep going. So let's look at 3. Well, this cell split 3, this ball also does not intersect this line either. So this is good. So this whole other subtree of 3, I don't have to check. Okay, so now let's go up to 1. Well, with 1, I do go over this line. All right. So I went over this line. So now I need to go and check something in this other half of the tree. So I go down to 2, and I say, well, let's look at the 2 halves of this 2. Well, this half of this tree, this half, the ball does not intersect. So I can skip this. I can prune this off. Now I need to go down this side, and I can say, well, let's say maybe this overlaps. Just to illustrate it. Okay, so I can't prune either side of this 5. But let's look at the closer one first. I can figure out which one is closer. So this side is closer, and I go and I find this other point. Let's call this P prime over here. And it turns out this one is closer. Okay, so now I can go and I can draw a new circle. And I have a new certificate. This is a better certificate. And now I can go and say, well, now that I found this, I said, now this might be the answer. I go back up to split 5, and I say, well, now the circle does not cross here. I don't have to check this whole subtree. and then I'm done. So now once I've pruned out all the subtrees that I know don't have the nearest neighbor, I know I found the true nearest neighbor, which is P prime. Okay, so this is not as simple as this original binary tree search, but I've still been able to prune out large parts of this tree I didn't have to check. And for larger and larger data sets, this is more effective. So does this make sense how this works? You first go and find the most logical point, the one in the same cell as your query, and say, this is a good guess. And then you go and you prune off everything else in the tree, recursively saying, I don't want to check these other things. And the better estimate you have, the better pruning will work. Right, so if you have a choice of two things to check, always check the closer one first, and you'll get a better, a better estimate of the closest. Okay, so good. So before I kind of move on to why this breaks down high dimensions, there are a couple other variants of things like a KD tree. There are things called so there's a quad tree. Okay, so the quad tree is similar here, except, and so this is in 2D, in 3D it's an octree. You think of a space, and every level of the tree you split into 4 different pieces. And the splits are even by space, they're not by the number of points. Okay, so now the top of the tree is 1, and then I have 2, 3, 4, and 5. So my data structure is 1, and now I've got this 4-way split. And 3 dimensions, this would be an 8-way split. In general, it's a 2 to the D-way split. Okay, and all the cells stay the same size. And I keep going until the cells are empty or they have, say, some small number of points. And sometimes I will get, I can skip some level and I can compress this a little bit. So this doesn't have the property that its height is log n, like before, because I could have all the points, almost all the points in one cell, so I'm not getting this divide by 2 property. But I get that the space is divided evenly. Here, the space may not be divided evenly, and I may have large sections between 2 neighboring cells. So it has certain advantages, and you can actually prove a bit more about this technique in terms of the efficiency, and in high dimensions give certain bounds. But in practice, this KD tree works better. And the reason it works better is the splits are adapting onto the data, whereas the splits are spatially defined. And so most data is actually not uniformly spread out. If the data was uniformly spread out here, the quad tree would probably work better. But data is usually there's some kind of structure in the data. There's some trend in it, or there's some patterns and clusters. And the KD tree will capture that and kind of adapt the splits to that. There's a different sort of tree that's called an R tree, which probably does a little bit better job in kind of fairly low dimensions, say 2 to 4 or 5 dimensions, at capturing splits than the KD tree. What this does is, let me try and draw a picture again here. So let's say the data looks like this. So what it's going to try and do is instead of splitting kind of based on these dividing lines, it's going to try and draw these rectangles around the data. So the R stands for rectangle. And it's going to try and find the best fitting rectangle that divided up the data. So I guess you started with one big rectangle, right? So you'd have a tree 1, and then you're going to have 2, 3, and 4. So you would split this way. So it automatically fits rectangles. And then you try and subdivide these points into various rectangles. And there are various policies on how to do this to try and maybe you want to avoid really skinny rectangles because it doesn't do the pruning as well, right? So you would do this, and so in kind of 2 to 4 dimensions, this works pretty well. And so if there are versions of kind of this B tree, which is this for really massive data that are designed to work with this R tree type structure. But this one kind of, because this rectangle structure is very rectilinear and high dimensions, if your data fit nicely in these sub-rectangles, this would all be great. But typically the patterns will actually look, something like this, and this is in 2D, but it's moving through high dimensions in some way, or it's not necessarily aligned with the coordinates. Yeah.
Would it be possible to do kind of like a layered k-means type of thing, where you do k-means for larger set and then smaller and smaller?
Yeah, actually, so actually this is pretty close to the state of the art. So I'll actually get to this. Let me move up this screen. Okay, before I get to the higher dimensions, I want to mention there's another trick you can do to kind of get this to kind of keep working as you get closer to 12 dimensions. And that's to, instead of finding the exact nearest neighbor, to get what's called the approximate, we'll call this epsilon approximate nearest neighbor. Okay, so if you have, so define P star, or actually let's define this function phi of P of Q of query point. And so this is going to be arg min of P in the set P of, and this is our data set of our distance between the. Okay, so this is the minimum, right? So this is what we would like to find, and we'll say that P is an epsilon approximate nearest neighbor if the distance from P minus Q is going to be less than or equal to 1 plus epsilon times Q minus phi of P. Okay, so this is the exact distance, and I've inflated it by a little bit here. So epsilon is some small parameter. Maybe if epsilon is 1, is the value 1, and that means it's no more than twice as far. If epsilon is, say, 0.1, then it's no more than 10% further. Okay? So, I'm giving up on finding the nearest neighbor. I'm willing to find some approximate nearest neighbor. There may be multiple of these options. Right? So this kind of turns out to be make a really big difference in when you get to start 5 to 10 dimensions. What's happening is that you're trying to fit. So you're always forced to kind of do these rectilinear, or these dividing by these half space type boundaries between these cells, but you're really searching in this ball. And balls don't fit very well by these flat edges, right? Think of fitting a ball inside a square. So at this point, to kind of illustrate this, I kind of want to give a kind of a neat point about high dimensions. So let's compare two things. Let's say a box which is going to be in the range of -1 to 1 to the power d. Right? So this is going to have d coordinates between -1 and 1, and we're going to call this box of d. And so the volume, the volume of this box of d is going to be 2 to the d. right? So this is growing exponentially in D. Okay, so this box may look, you know, so this is -1, -1. This is 1, 1, and this is the box. Okay, so now let me draw the largest ball that fits inside of it. Okay, so this is a ball where the radius is 1. Let's call this ball of D, which is going to have radius equals to 1. So now what is the volume of the ball called D? Do you know what was the volume of this? So in 2D, it's going to be pi r squared, right?
Yeah.
Yeah, so it's going to be pi times the radius squared, so that's going to be, that's pi. Right? In general, it's going to be pi to the d over 2. Okay, so we're growing exponentially here. But dividing by what's called the gamma function, which is d over 2 plus 1. And this is basically pi over d over 2 times d over 2 factorial. Okay? And so what happens, so this d over 2 factorial actually grows really fast. It grows faster than the pi to the d over 2. So when you get to about d equals 5, this whole value here gets up to about 5, and it grows from d from 1 to 5, but then it starts going down. And so as d goes to infinity, this volume goes to 0, actually. That seems strange, right?
Yeah.
The volume is going to 0. Well, okay, so how can the volume get smaller? Well, you're changing the units, right? So they're not really comparable. But what you're comparing against is one kind of, it's not a quarter, but 1 over 2 to the d of this box, right? A unit volume is 1, right? This is growing exponentially fast. This one is shrinking with respect to a unit volume. What's happening is the difference here in 2D is these corners. But when you get up to every dimension you add, you double the number of corners. In fact, these corners are actually getting bigger and bigger. They're getting a bigger and bigger percentage of the box. And so this ball is relative to the box is getting smaller and smaller. So I mentioned before, you want to generate these high-dimensional, these unit direction in high dimensions. So if you pick the unit, a point inside this box and normalized it, it's always going to be pointing towards one of these corner directions, right? And this actually, you know, you can understand why this is if you look at this Chernoff-Hofting bound that we talked about earlier on in class. Each of the dimensions is essentially these random variables, and they kind of approach the mean. And so what's happening is you're kind of approaching the mean, and you're getting some point where an average is going to be pointing out. There's a way of seeing it. But so what's happening, the reason why these sorts of things start to break down in higher dimensions is that you're trying to search for the smallest ball that just barely touches the closest point, but you're looking in the space of boxes. Okay, and the balls are doing a worse and worse job of fitting in the boxes. Even if you have the smallest ball that fits in the box, you have a lot of this overlapping. Right? So you're doing kind of, it's harder and harder to divide up the space. It turns out if you do this approximation, you shrink the ball just a little bit. Well, this turns out to really help a lot. You know, there's another kind of, some more mathematics you can go through, and you can see that if you look at the volume of the ball, more and more of the volume is getting closer to the boundary. Almost all the volume of the ball is very close to the boundary. So if you shrunk the ball a little bit, you're drastically changing what the volume is. So kind of shrinking it a little bit doing this approximation here is going to really help in this nearest neighbor search. You're kind of thinking, if you came just across, so if you think back, remember the first time I drew the ball, it kind of went over these two boundary points here. And then I shrunk it a little bit, and I was able to prune both of these whole subtrees because I was able to do that. This is, you know, this is not an uncommon thing to happen. Shrinking the ball a little bit will allow you to do a lot more pruning. So there's this, and so this has been studied fairly extensively. There's a pretty good software package if you type ANN into Google. It's not the top hit, but it's, you know, it's like probably the fourth hit. This is also the name of a stock, and it's a common name, and it's just this expression. You'll get a software package to approximate nearest neighbor. And this scales, depending on your data, between 8 and 20 dimensions. I know the guy who kind of maintains this. He said some people will come and say, it's fantastic, it works up hundreds of dimensions, and other people say it kind of stops working around 7 or 8. But so, yeah, so there's this software package that works pretty well. This is a good thing to try and use if you want to do this in practice for data that fits in memory. If your data doesn't fit in memory and you need to use some things like the B-tree, you're gonna, then this is kind of the edge of where, this is very new at this point on research, right? Trying to do these things. And there are various different techniques, people are weighing which one is better. Okay, so doing this approximate nearest neighbor, based on this KD tree and a few extra engineering tricks to get it to work, you can get up to maybe 12 dimensions, and this works pretty quick. You're going to scale roughly logarithmically with the size of the data. If you want to do it exactly in higher than 12 dimensions, you're better off probably just checking the distance to every point. You can do that very efficiently. You can write one for loop, and it will kind of run without any extra overhead, and you know that'll work better than any of these other structures. Okay, but what if we want to go to really high dimensions? Well, so the first, technique is this locality sensitive hashing, right? That we talked about before. So this was kind of in the, I guess, early 2000s. This was kind of when this came out. This was really the state of the art for doing this. And he said, well, you had to set this threshold value, and then you got everything that was within that threshold. Well, you can kind of do a binary search in that threshold. You can start small, and if your set is empty, then you kind of increase it by a factor 2. And if it's too big, then before you get too many things, you say, hold on, I'm going to stop, and then you cut it to a little bit. And you kind of do binary search on this threshold and find the nearest neighbor. And this does not depend, the runtime really does not depend on the dimension of the data. So it's, you have to look at every dimension in order to do it, but there's none of this exponential sort of thing with the dimension. But it's got pretty high overhead. So in the I think around, in the mid 2000s, say maybe 2007, people said, let's see if we can push these. So this, by the way, was in the 1990s. People were doing this ANN stuff. And it's still used today in So mid-2000s, people said, let's go back and let's see if we can look at this KD tree again. We know something more about the data. We're not searching. So this LSH was meant to work on kind of any sort of data. It has no conditions on the data. And we already knew that the KD tree was working better than the quad tree, which kind of had this uniform assumption. So there's something special about the data. It's somehow clustered, it's got these patterns in it. Let's see if we can exploit that. And so there are various ideas of how to adapt the KD tree. So then, so there are these KD tree extensions. And some of these date before these mid-2000s, but I'm talking about where people have actually engineered it and got it to work really well. So kind of the simplest, the first thing was this, this ball tree. And the idea here was to, and this actually works in any, this works in any metric space. A lot of the other things are designed mainly for Euclidean distance. And they probably work even better on L1 distance or L infinity if you rotated everything 45 degrees, because then your ball actually looks like a square. So you don't get this sort of phenomenon. You still get it, the rectangle, you get rectangles instead of squares, so it's not perfect. But the ball tree said, let's look at all the data that we have. Okay, and I'm going to look at all the data, and I'm going to pick a point in some way. Maybe I pick a point at random, and I'm going to draw a ball so it contains half of the points. And so then either I'm inside the ball or I'm outside the ball. And it could have been there are some points out here actually. So I got lucky with this one. But now these points on outside either side are both outside the ball. And now I recur either inside the ball or outside the ball. And all I have to do is measure the distance from a point. So I'm no longer drawing these lines, which in the space which is kind of going against this notion of a ball. I'm drawing a ball I'm comparing to a ball. I just have to measure the distance of my query. So if my query is here, it's less than the radius of this ball, and I recur inside. So this works in any metric space, and it's a very powerful technique. But this had this problem where sometimes you get data on two sides, and if you go outside, you're kind of not really working on this half of the points. So there's some better things you can do, and so there are kind of two approaches which people have started to understand from like a very fundamental level, which actually work well in practice. And so one is kind of a random directional split. So instead of picking X, Y, Z split and keep rotating,